name is Frank Sanders. I'm the head of the Telecommunications Theory Division at the Institute for Telecommunications Sciences, a laboratory of the National Telecommunications and Information Administration, NTIA, located in Boulder, Colorado. Over the past 30 years, we've developed a series of techniques for measuring emissions from various types of radio emitters. In particular, we've developed techniques for measuring emissions from radar transmitters. In this series of talks, I will begin by describing the fundamentals of RF measurement techniques, and I will culminate the series by describing our techniques for measuring emissions from radar systems, techniques that hopefully you can implement yourself. Accompanying this series of talks are notes available on our website and also NTIA reports that you may find useful. We hope that you will enjoy watching this series of videos as much as we've enjoyed producing them.
Welcome to the 16th ITS RF Measurement Seminar. This talk today is about resolving RF interference with reference to miscellaneous problems, problems other than those that are generated by the mechanisms that we've looked at up until now. And when you're looking at what I call a miscellaneous or a zoo category problem, you're going to have to, I think, normally eliminate co-channel interference or RF front-end overload first, and then work your way down to what the problem actually is. And so today we're going to start off by just doing a real quick review on the first two mechanisms. These are what I have encountered as the most common interference mechanisms. And given that any interference problem can be really difficult and expensive to resolve, there are some techniques that can make the analysis of the problem and the resolution of the problem relatively straightforward. So let's walk through it. Suppose that someone thinks that they have an interference problem. You've talked to them on the phone. Your management or your company decides that they really do want to investigate it as an RF problem. The chances are that they're either getting co-channel emissions, that is emissions on the receiver's fundamental frequency from some transmitter, or the receiver is developing a front-end overload problem. And again, just a quick review of RF front-end overload. What happens in this mechanism is a receiver is running at this frequency, but it has a low noise amplifier that responds over a much wider frequency range than the band in which it's supposed to operate. And we see its response here as low noise amplifier gain as a function of frequency. And some strong signal turns on, typically but not always a radar signal, which is at a frequency that is not only not on the receiver's frequency, but is not even producing typically any measurable emissions in the receiver's band. But when this signal goes up and turns on, the response of the low noise amplifier drops out, drops down, and the desired signal is lost. The other mechanism, co-channel interference, is probably what's thought of most typically as a classical sort of interference, and this is one in which a transmitter is in fact producing energy that is measurable and is high enough to cause interference to a receiver in the receiver's band and on the receiver's actual frequency. And these problems with co-channel interference can be mitigated to some extent by making sure that transmitter emissions meet spectrum masks. For radars, it would be the radar spectrum engineering criterion mask limit. But as I've said before, meeting a mask limit does not mean that interference cannot occur. It just reduces the chances that interference might occur. Now, there are less common interference mechanisms, but less common doesn't mean never. One way that a receiver can get interference other than what we've discussed is case penetration or feed-through, in which a strong radio signal comes directly into a receiver's circuitry, bypassing the antenna altogether. Another problem is one in which multiple signals being transmitted from a single site, typically a broadcast transmitter site up on a hilltop for television, FM radio, and land mobile radio signals, intermodulate with each other to produce two or even more than two radio signals. And two radio signals mix and they produce a third signal, or more than a third signal, can produce several signals, and those signals can affect a receiver. So those are called intermod or IM products. Another problem is when a transmitter's energy encounters typically a rusty metal object, typically somewhere near the transmitter, and that rusty metal object re-radiates energy. It behaves in a nonlinear way like a diode, re-radiates energy, and it will radiate that energy normally, if not always, on harmonic of the frequency that the transmitter is producing, and this is called the rusty bolt effect. So you have a tower or a fence near a transmitter. The tower or fence picks up the transmitter's energy. It re-radiates the energy at 2 times the transmitter's frequency, 3 times, 4 times, 5 times, and usually the odd harmonics are stronger than the even harmonics, so the 3rd, 4th, and 5th are stronger, but the so-called rusty bolt effect. And then finally, generation of unwanted energy inside a receiver RF front end due to some basically weird, unexpected physical mechanism that typically arises from either a bad design or bad construction or both of a receiver RF front end. And we'll look at that with some case histories here. Now, the basic ways to check these mechanisms are, in case of case penetration, to disconnect the receiver antenna while watching the interference in the receiver's IF and see if the interference energy is still present when you take the antenna off. And in fact, I've actually seen cases where not only was the energy still present when the antenna was removed, the power level in the IF stage went up when we took the antenna off and terminated it. So if you see that happen, you've got case penetration, and then you can work by getting better shielding for the case for the receiver. Intermod products can be diagnosed by the fact that they always fall on a frequency that is a function of 2 transmitter frequencies. We'll call them F1 and F2. And typically this occurs at broadcast sites, both, as I said, either for television, land mobile radio, FM radio. But the frequency of the interference will be equal to an integer m multiplied by one of the frequencies, plus or minus an integer n multiplied by the second frequency. And the odd-integer values, again, occur most commonly. Now, if the 2 frequencies are close to each other, if F1 and F2 are nearly equal to each other, this would happen with a cellular or land mobile radio system where one of the frequencies might be 861.1 and the other frequency might be 861.2. Then what happens is F1 is nearly equal to F2, and so the frequency of the interference becomes virtually equal to the sum of 2 integers multiplied by F1. And so we'll just take that sum as another integer k. So now this becomes virtually, but not exactly, equal to a harmonic of that frequency coming off that hilltop. So it'll look like maybe, for example, a 3rd harmonic of F1 when it's really F1 and F2 mixing together, but F1 and F2 just happen to be real close to each other in frequency. Now, the rusty bolt effect can be a little difficult to separate from intermod because, separate from intermod and also from a genuine transmitter harmonic. Bear in mind that transmitters themselves generate a 2nd, a 3rd, a 4th, a 5th. So we have 3 different ways of getting something that looks like a harmonic emission. Either the transmitter makes the harmonic itself, or the rusty bolt effect makes it, or intermod between 2 different frequencies that are close to each other make a signal that's almost, but not quite, on the 3rd harmonic. And in fact, one way to distinguish between them is that whereas intermod can only generate frequencies that are close to 2 times F1, 3 times F1, and so forth, the rusty bolt effect really will generate energy that's an exact multiple of some transmitter frequency. We'll see a case history, too, here where there was another clue to the rusty bolt effect related to this issue. So just bear in mind that if you see a harmonic, you have to figure out whether it's an intermod, whether it's coming directly out of the transmitter, or whether it's due to a rusty bolt effect. I will say that after 30 years of having worked on this kind of thing off and on, I've seen one genuine rusty bolt case. But there was one, so they do happen. And then finally, if you're getting the generation of unwanted energy inside the receiver RF front end due to some weird, unexpected physical mechanism, then there's no cookbook solution to finding it, but what you're going to have to do is eliminate all the other possibilities and then methodically, and I like to say, but inexorably, the way a glacier moves, slowly, methodically, but unstoppably, you will finally work component by component through the receiver until you isolate that interference energy inside the receiver and find the exact component, or, as we're going to see, a pair of components, where this problem is occurring inside the receiver. Now, just some classic examples that have involved co-channel and RF front-end overload interference that we've looked at over the years. Many years ago, there were satellite Earth stations that were located in Scotland, Alaska, Guam, Maine, Diego Garcia, which is in the middle of the Indian Ocean. And they were operating near 1.4 gigahertz. They were getting interference from what turned out to be an air traffic control radar, and That was due to unwanted energy coming out of the air traffic control radar and getting into the satellite system via the via that mechanism. So here we have the air traffic control radar, and it was putting energy out right on those Earth station frequencies. We also had a problem with co-channel interference years ago into Earth stations all over the Earth at 4 gigahertz due to unwanted emissions from naval air search radars. And we worked out an arrangement where the air search radars are able to function in such a way that they are able to avoid this co-channel interference when they're operating close to the coastlines of various countries. And then we have seen RF front-end overload interference at many different locations in many different situations, but one case in particular years ago, again, was at 4 gigahertz, again getting into satellite Earth stations all over the continental United States and in Hawaii and Japan. And this was due to desired emissions from an airborne radar that was tuned hundreds of megahertz away from the Earth station frequencies, but it was overloading the Earth station front ends. And of course, what they had to do there to solve that problem was to put band pass filters on the front ends of the Earth stations in order to mitigate that problem. And we've talked about that, of course, already. So I can't emphasize enough that when confronted with the need to solve an interference problem, a person needs to be methodical and needs to work systematically on each individual interference problem, look at it as an exercise in the scientific method and in the use of classical Greek logic to gradually work your way through. I have seen cases where people have, I think, thrashed around, kind of grasping at straws, thinking maybe it's this, maybe it's that. It's like someone who's trying to repair your car and they just start putting in parts thinking that eventually if they replace enough parts they'll finally solve the problem. It's very annoying, it's very expensive, it's very time consuming, and it usually ends up not working anyway. So instead of grasping at straws, randomly attempting solutions, why not, when all else fails, methodically eliminate all but one of the range of possible interference hypotheses that we've seen on the previous slides, using measurements and observations to find the answer. And sometimes, speaking personally, I think people do in fact try everything before they try being logical.
Sort of like reading instructions.
Like when all else fails, read the instructions. So, to help us understand how to identify interference mechanisms, and given that there's no one-size-fits-all method for doing it, I think it's useful to review case histories in which the mechanisms have turned out to be rather unusual, sometimes a zoo situation. And I think the very fact that we can and do and have isolated and identified these miscellaneous types of interference demonstrates that if a person is very careful and methodical in their approach, they should always eventually achieve a successful result. So today we're going to look at 2 case histories. And the first one involved interference from an air traffic control radar into a weather radar, and it turned out that the problem actually was either occurring or was a potential problem at locations all over the United States. The second problem involved interference at a single location from a television broadcasting transmitter into an Earth station. And at first it looked like it might be kind of a garden variety problem, but it turned out to be a little more complicated than one might have thought. So, case history number 1. Years ago, not that many years ago, a few years ago, a new class of airport air traffic control air surveillance radars began to be installed at locations across the United States. And it turns out that these radars were typically being installed at airports where weather radars were already operating, and the weather radars and the air traffic radars were both operating in the same band between 2.7 to 2.9 gigahertz. Now, normally that's not a problem because, as we've seen, normally because radars produce rather low duty cycles, although this radar does have a rather high duty cycle compared to some, the radars are able to successfully function through each other's pulse repetition rates by basically correlating on their own pulse repetition rates for returns, and not correlating on the other pulse repetition rates. But in this particular case, where these airport radars had been installed, there were at least 3 sites that were immediately showing problems in which the air traffic control radar was causing loss of data in the weather radar, and there were at least 20 sites around the country where they'd been co-sited where we knew that there was a potential problem. So what was going on? Well, we were brought in by the sponsor, the agency operating the weather radars, to examine the problem. This was what they would see on a weather radar display. They would see a strobe that was pointed off in the direction of the air traffic control radar. So there's no problem identifying what the source of the problem was. And these artifacts were contaminating the processing of the weather data. The Weather Service calls them products. They were contaminating their products. Our task was, first and foremost, to determine a method to end this interference problem for the sponsor. The sponsor, in this case, was the agency operating the weather radars. What we needed to do was demonstrate an actual solution at one of the sites where the interference was occurring. But to do that, we needed to know, of course, what the interference problem was. And then, having identified the problem, having found a solution, we needed to be able to show that we could implement whatever the solution would be at sites all over the U.S. that either were or could experience this type of interference. So our approach was, first of all, to identify the interference mechanism. Was it co-channel, front-end overload, or some other type? And then, once we had identified the mechanism, test a solution. Now, if we know the mechanism, for example, suppose it's front-end overload, we know that we'll need to put a filter on the front end of the radar experiencing interference. If the problem is co-channel interference, then we'll have to put some kind of filter into the radar, in this case the air traffic control radar, that's generating the interference. In any event, we don't want to waste time testing solutions. We do not have a lot of time when we show up at a site to get this work done. These problems are very expensive to solve. They cost a lot of time in terms of hours for people to work on them, and time at these radars is expensive and takes time away from radar operations. So we need to work in a very timely fashion at these sites. And then finally, I think it's important to report results, because the only way that this work typically does any long-term good is to explain it to the sponsor, first of all, so they know what's going on. They believe that you have found the solution and they'll implement it. And secondly, to get the word out to the larger engineering community via publications and talks like this. So the diagnostic procedure at the site is, first of all, carefully trace out and measure the energy that's coming from the source. We need to look, and we've talked about this in the earlier talks, I'm going to walk through it quickly here. We need to look at the radiated spectrum and time waveforms coming from the interference source. We need to measure the interference spectrum and time waveforms inside the receiver that's experiencing the interference, and we need to look, first of all, at what it looks like when it's coming right in through that antenna on the receiver. And then we need to work our way down along the path inside the receiver, typically down to the receiver's IF stage, to see what might be going on inside the receiver. And, of course, we look for our front-end overload effects up at the LNA output up here at the front end of the receiver. We've discussed that previously. And when we're looking at the energy and time waveforms in the victim receiver's IF stage, as we've seen in previous talks, we can look for the front-end overload effect. We did that in a laboratory session that we did on our last talk, and we can look for other indications that the energy is due to unwanted, which is either out-of-band or spurious emissions. We talked about this last time, so I won't belabor it. Here we have the high-power radar pulse coming in right here. We're watching the effect of the high-power radar pulse in the victim receiver's IF, and we see the output of its low-noise amplifier dip right after the radar pulse hits. In fact, it's dipping even when the radar pulse is hitting, but at this point the radar pulse is masking it. But depending upon how hard the radar pulse hits it, we get these dips that go deeper and take longer and longer time periods to recover. This is the classic front-end overload, and again, we've talked about it before.
Desensitizing it.
Desensitizing the front end of the victim receiver, and more details in NTA Report 94-313. Now, if, on the other hand, we're dealing with co-channel interference, where an unwanted, an out-of-band or spurious emission, typically from a radar, is getting into a receiver on the receiver's desired frequency, then here's what we'll see. We won't, or first off, here's what we won't see. We won't see the radar pulses in the victim receiver looking like this, which is what they look like when they come out of the radar that's transmitting them. There's a nice clean pulse that's a few microseconds long. Here's a short radar pulse, nice clean pulse, a few microseconds long, and this is what these radar pulses look like if you see them on their center frequency. That's the frequency of the radar generating the interference. But, this is important, if we're seeing energy in a pulsed emission spectrum not on the frequency of the transmitter that's producing the pulses, but off-tuned from that transmitter frequency by 200, 300, 400 megahertz, the receiver is only seeing a small subset of the total set of lines in that emission spectrum. If you observe a small set of lines in the Fourier spectrum, you do not, in the time domain, form a nice, clean pulse envelope. Instead, you form a pair of pulses at the leading and trailing edges of the pulse. And these are vernacularly called rabbit ears by technicians. And you can do this mathematically with a simulation in, for example, MATLAB. You can actually do the convolution of a pulsed emission spectrum with a narrow bandwidth that is not tuned to the center frequency of the spectrum, and you'll see this effect occur. It is forced by the mathematics of waves. It's forced by the mathematics of the Fourier transform. And so if you're seeing this in the victim receiver, you're seeing a pair of pulses that are the so-called rabbit ears, or sometimes you do see a little bit of activity between the rabbit ears on either end, but it still looks very, very raggedy. It should look like that. Instead it looks like that. Or it should look like this. Instead it looks like this. You're seeing off-frequency energy, off-frequency that is relative to the center frequency of the radar producing the pulses. That's an indication that you're getting co-channel interference, that you're seeing unwanted emissions, out-of-band or Spears emissions from that interfering radar in the receiver that's experiencing the interference. And again, this is discussed more in NTIA report 94-313. So, for this particular case where we were working for the sponsor, the first thing that we did was, in fact, to measure the radiated spectrum. The radar producing the problem, of course, was identified by the direction that the strobe was pointing on the display. We used the procedure in NTA report 05-420 for making RSEC measurements. And the one thing that I want to note here is that it is always essential when making an RSEC measurement to select the proper measurement bandwidth. As we've seen in earlier talks, if you pick the wrong bandwidth, in particular if you pick a bandwidth that is wider than you should pick based upon the criterion that are discussed in this report, you'll make the spectrum of the radar look worse than it really is. You'll make its unwanted its unwanted emissions look higher relative to its fundamental power than they really are. The measurement system looks like this. We were 489 meters away from the air traffic control radar. We brought the power in through a parabolic reflector antenna 1 meter in diameter, in through a variable RF attenuator, in through a tunable YIG bandpass filter, into a low noise amplifier, then down into a spectrum analyzer, and running the whole thing under a computer, stepping our way through the spectrum. This was the vehicle, the NTIA RSMS-4 that we were using to do the measurements at the site. We had the antenna mounted up here on the roof of the RSMS. And the two radars were themselves only a half nautical mile apart. That, by the way, was a bit of a mistake to begin with. The two agencies involved with these radars hadn't maybe coordinated as well as they wished they had later. But the radars themselves were only a half nautical mile apart. As I said, we were only a few hundred yards away for our measurement. We did two independent radar measurements with two independent measurement systems and two independent sets of software, partly because we were testing one of the sets of software and hardware, but partly because we like to be able to verify that we're getting the same result with two systems, indicating that what we're seeing is the real, quote, the real, unquote, spectrum. And we did get identical results with those systems. The airport radar was using a 4 megahertz wide chirped pulse, swept frequency pulse, with an 89 microsecond pulse width, which was actually paired, as it turns out, with a second pulse. And if you go to report 05-420, the appropriate RSEC measurement bandwidth to use for that radar would be 212 kilohertz or less. Now, the weather radar transmitted two different pulse widths, 1.5 microseconds and 4.5 microseconds, which correspond to IF bandwidths that are 1 over those pulse widths, which are 680 kilohertz and 222 kilohertz. So we decided that we needed to measure the air traffic control radar spectrum in that bandwidth, which corresponds to that mode for the weather radar, and in this bandwidth of 222 kilohertz, which corresponds to the weather radar second mode. And it just so happens that 222 kilohertz is nearly the same as 212 kilohertz, so we could kill two birds with one stone by letting this measurement count for the RSEC measurement as well.
Was this an XRAD radar, Frank, for the Weather Service?
The Weather Service, yes.
Was that one of their state-of-the-art units? Or?
Yes.
Okay.
Yes. And so we used measurement bandwidths of 680 kilohertz, and we went on down to 200 kilohertz for the second mode, because you can go wrong by being a little too wide, but you cannot go wrong by being a bit too narrow. So 200 kilohertz is a bit narrower than the ideal 212, and it's a bit narrower than the 222, but these three numbers are all pretty close. So we did the measurement in these two bandwidths. We get this emission spectrum. When we measured in a 200 kilohertz bandwidth, we got this emission spectrum. When we measured in the 680 kilohertz bandwidth, we got this emission spectrum. This brings home my point about measuring in a wider bandwidth makes the spectrum look wider. We didn't touch the radar, we just measured in a different bandwidth. Now, the bandwidth measurement that we need to apply under the RSEC mask is the 200 kilohertz measurement, and it easily fits in under the RSEC mask. And we see out here at the ultimate suppression level that this radar is way down below. It's 10, 20, 27 dB below the mask limit in terms of meeting the RSEC. So they're meeting the RSEC mask limit. And we also see that at the weather radar frequency, which is not quite on this graph, that again, in either of the weather radars bandwidths of 680 or 200 kilohertz, that the emission level of the radar relative to its fundamental power level is down anywhere from 94 dB in the 680 kilohertz bandwidth to as much as 103 dB in the 200 kilohertz bandwidth. So you would think that that would not be enough power to cause co-channel interference into the weather radar. So we put that information aside. We've got it. We've seen it. Now we move the measurement system that we had over to the weather radar. We set it up at the top of the weather radar tower. This is the part of the parabolic dish that the weather radar uses. And we start to measure the energy from the interfering air traffic control radar in the front end of the weather radar. Here we have a spectrum analyzer. We have an oscilloscope with a detector. We have a computer to run our measurement system. And we measure this energy right at the antenna output. And then we'll follow this up by going downstairs and measuring energy inside the weather radar, inside its IF stage. And that was our plan, and that was what we did.
So you were in the receive-only mode at this point?
So this radar at this point, this is the weather radar, is in a receive-only mode at this point. And when I say that these things are expensive to work out, we had approximately 8 people from the Weather Service and the FAA, along with 3 or 4 people from NTIA at this site. You got 10 people who probably cost $180 an hour. That's $1,800 an hour we're burning on labor. We do not have all day to just sit around kind of thinking about what we're going to do. So we had an attack plan before we came in, and we exercised that plan walking right on down through it as we go. We also spared no expense on graphics. This is the front end of the weather radar. It has a 28, well, you know, this is what I sketch on the way. We have a 28-foot dish. It comes into what's called a passive diode limiter, a PDL. Remember that term. It's going to come up again here soon. Then into a bandpass filter that the Weather Service called the EMI, electromagnetic interference filter, EMI filter, then into the low noise amplifier, then down into the IF stage via a mixer. Now, a word about this. So far in this series, we've never talked about diode limiters. Where the LNA is used to improve the sensitivity of a receiver, and the bandpass filter is used to reject strong energy that is not in the desired RF band of the receiver. The passive diode limiter is installed to protect the low noise amplifier from physical burnout in the event that this receiver is hit by an extraordinarily high power level. Not a power level that merely causes the LNA to gain compress, but a power level high enough to literally burn out the LNA. I have never actually seen an LNA get burned out at its front end by a strong signal, but it's a concern. So, the way the limiter works is it passes energy through as long as it does not exceed a certain threshold. But if energy coming into the diode limiter exceeds a certain power threshold, the diode limiter turns into something that looks like an electromagnetic mirror. It cuts off energy in the forward direction entirely. It stops the energy right here, and it actually reflects, or I will say is supposed to reflect, that energy back out of the front end and not allow the energy to move downstream inside the system. Now bear in mind that where the bandpass filter is in fact an electromagnetic compatibility feature, in that when it is operating successfully, the whole radar operates successfully. The diode limiter, if it functions when it's hit by high energy, terminates the radar's operations at that point. For as long as that interference energy is hitting it, the energy that is coming into the front end is all reflected back out, and the radar is not getting any returns. So they'll lose radar returns entirely if the diode limiter kicks in, but the idea is that it's better to lose the radar's functionality briefly or momentarily when the limiter kicks in than it is to burn out the front end low noise amplifier.
Would there be any reason, Frank, to put the limiter behind the filter?
Yeah, the question is there a reason to put the limiter behind the filter? Well, that's a good question. It turns out that, not to give too much away before the movie ends, this is supposed to be here.
Oh, okay.
But the engineering blueprints did in fact show it here, and they did in fact put it in there when they built the radar, so they followed the plan, but the plan was wrong. There's no need to protect a bandpass filter from high energy. You cannot burn out a bandpass filter. Well, if you burn out the bandpass filter, you better be in a bunker, because something's going horribly wrong at the radar site.
Direct lightning strike.
Right.
I was just
So
going to
this
ask,
needs
is
to
this
be over
intended
here.
for direct lightning strike? Is that the intent, or
Not
not,
really lightning strikes. The Navy uses them. They feel, although this is weather radar terrestrial, they feel it protects
The
them from
problem I see
strong
with that
incoming
picture,
signals.
Frank, is you put that limiter in front of your filter. I mean, you're exposing it to a much broader band of frequencies, and hence much more severe nonlinearity.
Well, that's another good point that you bring up, Bob. By putting the limiter here, it sees all the energy in all the world at basically all frequencies from virtually zero up to however high this responsive microwave part of the spectrum. Well, actually, the waveguide cutoff would terminate it below a certain frequency. But anyway, yes, it sees a lot of energy. Now, if you put it over here, it would only see the energy that would come through the EMI filter. And of course, again, that's the energy you worry about getting into the LNA. And that's really the energy that you want to limit. So again, right, that's another reason to put it. We'll see a third reason why this limiter should be here and not here. But okay, so here's what we measured at the weather radar antenna output. You've already seen the radar spectrum measured with our vehicle sitting out in the open. Now we measure this energy coming through the weather radar output, and I am going to back up a couple of slides here so we can get our feet underneath us. The radar, the air traffic control radar, is operating at 2860, 2860 megahertz. Now, what we see at the weather radar antenna is the air traffic control radar at 2860 megahertz. Great, no problem. The weather radar is operating over here at 2895, and that's how much power we see coming in through that big parabolic antenna, minus 41 dBm in the measurement bandwidth of 680 kilohertz, peak detected. Okay, now walk down through these. This is a close-up look at the weather radar's frequency at the antenna output. We are seeing some energy here from the radar, but not a lot. Now, we looked at the passive diode limiter output, and then we looked at the output from the bandpass filter. Mine, and literally, we did this one. We said, wait a minute. Did we get this right? Yeah, we got it right. Okay, hold on. Minus 30 dBm at the output from the filter. Now I'm going to back up a slide. Minus 50 dBm, 20 dB less, coming out of the diode limiter, which is at the input to the filter.
Cool.
See the problem? What now? I mean, I literally said, what? Wait a minute, hold it. All right, hold on. Okay, so now we're thinking. Now I'm going to jump back up, and we check this a couple times. Nope, it's right. Okay, and then we go to the LNA. Well, of course, the LNA is amplifying that energy, so sure, of course, that goes up. No problem there. So now we used our secret weapon, which is our field notebook, and we've got this diagram drawn, and this is what we drew right at the site. And these are our data records. File 2, records 4 through 7 were taken right here at a coupler, right after the parabolic antenna, a 20 dB coupler. And we measured right here, and we measure here at the input and output to this passive diode limiter. We see minus 50 dBm here, minus 60, depends upon how you detail on how we did the measurement. But then we go to the output of the filter, and we see more energy than we had coming in to the filter. And the filter is a passive device. There's no power source. So my remark at this point was, we're going to be rich beyond our wildest dreams, because we found out how to finally make more power come out of a device than we put into it.
Get your patent also.
Well, okay, maybe not. Yeah, time to patent. Nobody move until we patent this. All right, what's going on here? This was just weird. All right, so now we go back, and instead of looking at just the weather radar's frequency, we look at the spectrum from 2820 up to about 3 gigahertz at the passive diode limiter output. And again, we see this thing looking pretty well behaved. There's the radar's energy, the air traffic control radar, at its frequency at 2860 at the output from the passive diode limiter. Okay, good. That's what we ought to see. And we note, by the way, that it's not coming up high enough in power to really make the diode limiter kick in, which is fine too. Okay, so far so good. Now we look at the output at that bandpass filter. output. There's the radar's frequency at 2860, and this energy has gotten redistributed. Redistributed. Now we have all this energy coming out. It's coming out at such a high level that it's actually illuminating the shape of the bandpass filter. We're seeing the shape of the band. It's like we're illuminating the bandpass filter with a noise diode. And to go back a slide, that was what came into the filter at its input. That's what's coming out of the filter as output. And these two are at the same scale and same frequency range, these two slides. Well, all right, that's weird. So now I superimpose them on the same graph. That's what's coming into the filter at the output of the diode limiter, and this is what is coming out of the filter. Okay, that's just weird. So somehow, in quotes, somehow the disaster happened. Somehow this energy is getting redistributed, we realize, from this distribution in the spectrum into this distribution in the spectrum due to the way that this diode limiter is somehow functioning in conjunction with the bandpass filter.
And you recognize, Frank, that nonlinearities have ruined many lives.
And yes, nonlinearity sank the Titanic. So yeah,
and wreckage all over the
yeah,
place.
right. And one comment here I'm making passing again. These are a couple of photocopies out of my notebook. I think that in a case like this, a documentary record they take in real time. Personally, I prefer to write it down. I can do it. I can write faster than I can start typing stuff on a little keyboard somewhere. Is just critical. You can come back to this years later and look at exactly what happened, or you can come back to it 10 minutes later and look at what happened, so that you can really understand. Here we are, at the top of the page. We have the names of the two radars. We have the date. We have the time, 3:45 p.m., 4:30 p.m., and we're walking and we're showing here how we're walking down through this. Here are the data that we're recording. Here's the file, the record, the bandwidth, and comments. We're walking right down through it so that we can always go back to this and literally look at it and say, okay, here's what we did. Because I guarantee nobody on this planet can remember all this. You might think you will, but you won't. So I think a notebook is a kind of a priceless thing to have there. It's a kind of a secret. What's your secret? Well, my secret weapon is a $1.22 pen from King Soopers and a $3 notebook. So here's the passive diode limiter. Here's what it actually looks like. Here's the bandpass filter removed from the radar's front end. We looked at these two devices and how they function independently, and they function just the way that the manual says they should. You put them together, they have a funny behavior when you put this onto the input of that. Now, I'm going to walk through this quickly. At this point, we kind of know what the problem is in terms of how they interact. We said we're going to really sort this out. So this is where, again, time is running. The clock is running. We've got to keep things moving, but we need to know what's really going on here. So we look at the EMI filter output when we take the diode limiter out of the path entirely. So now it's just an antenna going into the filter. Now it behaves the way it's supposed to. Here we look at the spectrum at the limiter output when we put the limiter after the bandpass filter where it, Bob, as you said, ought to be. And again, it works the way it should. This, by the way, turns out, again, not to jump too far ahead, to be basically our recommendation to the sponsor is you need to move that limiter to where it's after the filter, not before the filter. But here we do a graphical comparison when we have the bandpass filter and the diode limiter in various different arrangements. Here's what we've already seen for these two curves, where we have these two components in place the way that they built the radar. Here is what we see when we put the diode limiter after the bandpass filter, and everything behaves the way that you think it actually should behave if you put the limiter in after the filter. So, not to belabor the point too much, we also looked at what was going on at the LNA output. This the sponsor insisted on. Said, I want you to look at the LNA output. Said, okay, fine. Because at this point we know that that's irrelevant, what's going on at the LNA output, but fine, we'll do it. And then we experimented with some things. We put a notch filter on the air traffic control radar at the frequency where its energy was getting into the weather radar. So here we're notching the air traffic control radar. So now we had to go back over to the air traffic control radar site, put a notch filter on it that notches its unwanted emissions right at the weather radar frequency. And sure enough, the notch works. In fact, you could tune the notch back and forth and watch that go up and down while you're talking to somebody on a cell phone or a handy-talkie between the two radars. Then we went down into the IF stage of the radar. We looked at what was going on inside the IF stage. I'm not going to belabor it here except to say that we're very thorough. We're walking our way through this, going to make sure that we get everything right here. And here we see what's going on inside the IF stage of the radar when we have the diode limiter followed by the filter followed by the low noise amplifier. That's how they built the radar. And you get this high energy inside the radar's IF at 55 megahertz. Then when you put the limiter between the EMI filter and the low noise amplifier, where it really ought to be electrically, you bring this interference level down by 10, 20, 30, 40, 45 to 50 dB. 45 dB for sure. Okay, this is the time domain. This is the pair of pulses that are coming out of the air traffic control radar. A short pulse followed by the chirped pulse observed with a detector hooked up to an oscilloscope at the weather radar's IF.
So you had enough bandwidth in your scope to capture the pulse.
Right, to capture both.
Okay.
And we don't see that overload characteristic. See that, right? We don't see that dip occurring in there. If overload were occurring, we'd see the dip, because we're still worried that overload could occur. Just because some other mechanism is occurring doesn't mean overload can't occur. So we check to make sure. But no, these are not overloading. The weather radar's front end, so we're good on that. And then here we just show some comparative graphs where we looked at different arrangements of the limiter followed by the filter followed by the LNA and so forth, and we also tried putting a supplemental filter on the air traffic control radar to reduce the air traffic control radar power at the weather radar's IF stage even more than it already was. And this is the effect of putting a notch filter into the weather radar spectrum. See, we bring that energy down. Here's the long and the short of it. This is the air traffic control radar energy in the weather radar's IF. And even this causes some degradation to the weather radar, but it doesn't cause the strobe, and it doesn't cause as much degradation as it does when you have the limiter in the wrong place. Put it another way, once you put the limiter where it belongs between the filter and the low noise amplifier, you now bring this energy in the IF down by 10, 20, 30, 40, again, 45 to 50 dB, but the Weather Service wanted it reduced even further. And for that, we had to put a filter on the air traffic control radar that brought it down by another 10, 20, 30, almost 40 dB. So now, if we combine these two actions of putting a filter on the air traffic control radar and putting the limiter where it belongs, now we can bring everything down by 90 dB or so.
One question.
Yeah.
Now, when they had the interference problem, they saw it intermittently, I assume, because the two antennas were passing each other periodically.
Right.
So we bore-sighted them, right? So that you could
So
look
we,
at this concept.
correct, Randy. So we bore-sighted. Right, exactly. Well, we bore-sighted the weather radar, and yes, we did bore-sight the air traffic control radar, which we could do because that radar had not become operational yet. So we did stop both the rotations, and we physically moved the antennas by hand until they were lined up on each other. Right. We could have done this with the two antennas rotating, but it would have been much, much, much slower as a process, and therefore would have made the whole problem much more expensive to solve.
Like on the last slide where you showed the pulse shape, we would have had to wait a long time to try and look at the interference.
Because we'd be looking for either main beam to main beam coupling, which would occur rarely, or at least main beam on the weather radar into the side lobes of the air traffic control radar, which would occur about every 30 to 60 seconds, which is still awfully slow. Right, exactly. So to get this, yeah, we went ahead and bore-sighted them. Right, exactly. Good point. Okay, and again, we tried retuning the we tried retuning the air traffic control radar. That didn't have much of an effect. You could put, as long as the notch was installed at the weather radar's frequency, retuning the air traffic control radar had very little effect. So the problem was not to get the air traffic control radar retuned. Time domain, won't belabor that. Okay, so conclusion. With the nonlinear behavior in the weather radar's RF front end having been corrected by moving the limiter to where it belonged, and with the efficacy of putting a notch filter onto the airport air traffic control radar having been demonstrated also, the problem now was simply reduced to finding a notch depth, the amount of attenuation that would remove the interference effects from the weather radar, basically to the satisfaction of the sponsor. We did do additional tests that I'm not going to go into here to gather weather radar data at a whole variety of interference noise levels by changing the notch depth so that we could find a specification for that notch filter for the air traffic control radar that would satisfy the sponsor. But the annoying strobe effect always disappeared as soon as we put a notch onto the air traffic control radar and got that limiter into the right place. And basically, until we understood that bizarre behavior between the limiter and that bandpass filter, no other mitigation technique could be effective. Another team had already been there from another place before us and had not been able to figure this problem out. And the reason was they had not been able to find that funny behavior between the limiter and the filter, and until you found that, you could not solve this problem. It was going nowhere. So the key, again, was to be methodical and walk our way through it. And we did recommend to the sponsor that they put out a change order for all their weather radars to move those diode limiters into a location between the filters and the front-end low-noise amplifiers, so that all of those co-sited localities in the U.S. would be protected from this problem. Okay, second case history. Around about 2000, a U.S. government earth station began to experience interference effects that were coming, as it turned out, from a hilltop a few miles away from the earth station, where energy was originating from a variety of television and FM broadcast signals. And they isolated the energy pretty much the same way the weather radar did. They actually aimed their earth station dish over to the hilltop and used its narrow beam width to isolate the place where the interference was occurring in terms of azimuth on the horizon. In fact, the whole problem came up because they would lose data that they were supposed to be getting whenever they pointed their antenna in a range of directions over in one sector of the horizon, and they eventually looked in detail and found the exact location on the horizon where this problem was occurring. So that part they identified for themselves. They asked us, OSM and ITS inside NTIA, to identify the interference source for sure. And we were given access to the earth station, but no coordination was performed initially with anyone who was connected with the broadcasting site, pending identification of what this interference signal really was. So the pertinent fact to know here was that the earth station frequency was about 3 to 4 times higher than the television broadcast signals that were coming from the hilltop. And we knew that those broadcast signals were generating enough power to potentially cause front-end overload of the earth station receiver, but we also knew that broadcast signals can and do generate interference harmonics coming right out of the transmitters that could also cause problems that were co-channel to the earth station, because the earth station is about 3 to 4 times the frequency of the broadcast signals. So if you happen to get a harmonic at just the wrong frequency, yes, it could happen due to co-channel interference. We weren't clear before we got to the site whether there was any RF attenuation. I didn't mean RF attenuation. That's RF bandpass filtering present on your station front end. That needs to be changed. That's bandpass filtering, not attenuation. I'm so embarrassed. So on-site measurements would be needed to performed to eliminate, again, one hypothesis after the next until we have only one remaining. We went to the site twice. The first time our scope was limited to just determining what the interference source area was, what the likely identification of the transmitter was, and the likelihood of whether RF front-end overload was occurring versus co-channel interference. For the second trip to the site, we were asked by the agency that time around to do everything possible to try to actually resolve the interference problem. So for the first trip, again, same steps basically. We're going to find the source. We're going to measure the spectrum of the source, just like we did in the case history you just saw. We're going to measure it at its fundamental frequency, and we're going to measure in particular the amount of power that's coming out of it at the frequency of the earth station. We're going to identify the presence of RF front-end filtering, if any, in the earth station RF front-end. We just couldn't tell by talking to people on the phone and getting some of the diagrams. It just wasn't clear. If no filter turned out to be present at the earth station, we were going to insert our own filter that we brought with us. And then we could draw, and then from that point we would draw conclusions about where to go from there in terms of tracking down the interference mechanism. So during the first trip, we did identify the source. It was a particular UHF TV station signal. Its third harmonic was very close to, basically on, the earth station's frequency. Okay. Now that's a mathematical statement. I'm not saying how high the harmonic is. I'm just saying that if you multiply it by 3, yes, you got the earth station frequency. We did spectrum measurements of the TV signal, and those did indicate that the energy coming from the hilltop at the third harmonic did meet the FCC emission mask limits, but it was kind of marginally close in terms of whether it might or might not cause co-channel interference into the earth station's receiver. So at this point, we're thinking it's possible that it could be a third harmonic out of the transmitter, which has just enough energy to cause interference right on the ear station's frequency. As for RF front-end filtering, they did have a filter installed on the ear station receiver, so we knew that RF overload was eliminated as a mechanism. However, given the close proximity of the broadcast hilltop to the ear station and the high power of broadcast signals, we were concerned about the possibility of case feed-through, receiver feed-through. So we did, in fact, disconnect the ear station antenna, and we did observe the IF of the ear station receiver when we did this, and we wanted to see whether or not we saw the TV signal's interference go away when we disconnected the antenna on the ear station. And it did go away when we disconnected the ear station's antenna. So that eliminated the issue of case penetration. So now we know it's not front-end overload, we know it's not case penetration. So now we're looking at energy that's got to be actually on the ear station's frequency that's coming in through the ear station's RF front-end. And it seems to be somehow tied to a third harmonic of this particular television station over on the hilltop. We were able to identify the television station signal due to its spectrum. So what was the source? Well, we told the agency at this point, at the end of the first trip, that it could be due to a harmonic emission coming right out of the TV transmitter, or it could be intermod that was occurring between the TV signal and other signals on the hilltop, where one of the other signals would have to be pretty close to the TV signal and would do the mixing such that we would get an output that would be pretty much on that third harmonic. Remember the equation, an integer times F1 plus or minus an integer times F2 generating the intermod? Well, here F1 and F2 would have to be pretty close because we're getting almost, or exactly as it turns out, a third harmonic frequency of that television transmitter. But there were some oddities that we did note concerning that third harmonic energy that made us think, and we put this in writing, that it might not be coming out of the TV transmitter. It was a loose end, as they say. The loose end was that the entire television station emission, and this is an analog signal, so it's the audio carrier, the video carrier, and all the information in the spectrum in between those two carriers, and 4 additional signals that were up on that hilltop were all being translated in frequency, not multiplied. Okay, what's the difference? The difference is you got 2 signals in the analog TV transmission that are 4.5 megahertz apart, audio and video carriers. If you take a third harmonic of both of those, you multiply this first signal by 3 in frequency, you multiply the second carrier by 3 in frequency. Given that they start off being 4.5 megahertz apart, if you generate a third harmonic of each of those, the third harmonics would be 3 times 4.5 megahertz, which is 13.5 megahertz apart, but we didn't see that. We saw the audio and video carriers still 4.5 megahertz apart at the third harmonic. See, that's weird. Okay, that shouldn't have been happening. And so we said in writing that this meant that the emission from the transmitter hilltop was some kind of result of both some sort of third harmonic production. I'm covering up a few of the details here in the interest of time, and some kind of a mixing phenomenon of some sort. We just weren't sure what. But the scope of our initial visit had been satisfied. So we basically left at that point with that information for the sponsor. The agency then worked with the broadcaster to install a third harmonic filter on the TV transmitter. Now, as I say, it wasn't clear at that point that the transmitter was producing that third harmonic from inside its guts. We had this indication that the energy was not coming from inside the transmitter's guts. In any event, because the TV transmitter spectrum, as we had demonstrated, already met the FCC specs, the agency operating the ear station provided the filter for the station, but the broadcaster agreed to install the filter. And this is no little filter you carry around in your hip pocket. This filter was what, Randy? 6 feet long? Weighed 100 pounds? It was huge. I mean, it was quite the little engineering project to get it installed. But having installed the filter, the problem persisted. So we got another phone call about 2 years later where people basically said, "What's going on here?" And we said, "Well, I mean, we know as much now as we did 2 years ago. You've installed the filter. Again, this confirms, since you installed a filter and the problem didn't go away, that the third harmonic energy apparently wasn't coming from inside the transmitter's guts. It was coming from somewhere else. It was not a third harmonic being generated inside the transmitter. So we go out for a second trip. This time we had access to the broadcaster's transmitter and the broadcaster's personnel. We measured the third harmonic power coming out of the transmitter via a hard line right on its front end, not radiated, right on the hard line. And we did that before the third harmonic filter that was inside the station and at the output of the third harmonic filter, kind of like what we had done in the case that I cited previously. Having done that, we were able to establish that the power that was coming out of the transmitter at that filter output was tens of dB lower in level than the power that was being radiated on the frequency of, as it turns out, the video carrier of the TV transmitter, radiated from the hilltop. Okay, so we look at the hardline output at the transmitter's filters output up on the hilltop with a hard line hooked in. We see a certain power level relative to the fundamental of the broadcast signal. We know that's what's going into that antenna of that broadcast signal. We get that level. We then look at the level that's being radiated from the hilltop, and we're measuring about 2 miles away, and we see more energy coming off the hilltop, being radiated off the hilltop, than is coming out of that transmitter. But we correlated it and knew it was a transmitter because we could turn off the transmitter, and we did turn off the transmitter, and the energy went away when we turned off the transmitter. Once again, we're rich beyond our wildest imagination because once again we found a way to generate energy from nothing. Apparently. Again, probably not. Okay, what's going on? So either the energy is originating via intermod, or there was this. It was an exotic possibility, one we had to consider. Maybe energy was radiating out of the TV transmitter cabinet directly over to the transmitter earth station, bypassing the antenna path altogether. It's possible. They were using big high-power tubes like klystrons in there. It's unlikely, but possible. Well, how could we distinguish between those two possibilities and the third possibility, which is the rusty bolt effect? Well, first of all, we eliminated the possibility of radiation directly out of the cabinet by going back to the earth station, putting a spectrum analyzer on the earth station IF, aiming the earth station at the TV station, looking at the interference coming into the earth station, in the IF stage of the earth station receiver with a spectrum analyzer, then calling over to the broadcaster and having them turn their station off the air, shunt all their power into a dummy load for about a minute, which meant that they literally went off the air. And we said, what about that? And they said, oh, we're just broadcasting novellas right now, and they'll miss a critical moment, but there are critical moments every couple minutes, so it'll be okay. So they shunted the power into a dummy load, so it's not radiating, and we're watching the IF over here with the antenna pointed into the earth station, pointed into the TV station to see whether or not we're getting energy right out of the case, right out of the transmitter case. And what happened was the interference did not occur. The interference went away when the TV transmitter went into the dummy load, so that mechanism was actually eliminated. Okay, so good. That's another one. That's another one down. Now, so now we're down to either intermod or the rusty bolt effect. Now, in principle, you can calculate all the possible frequency combinations for a given hilltop, given all the transmitters on the hilltop, and figure out whether any of them could give the same value for the frequency of interference as what you're actually seeing. But for this hilltop, the solution is actually quite a bit simpler. I had a glitch with my text here. Sorry. Whoops. Back. Remember that loose end that we've talked about? Well, if the intermod were occurring, although it could generate power nearly on the third harmonic, it couldn't generate power exactly on the third harmonic. Because, remember, it's m times f1 plus or minus n times f2. F1 and f2 could be nearly the same, but they can't be the same coming off of the hilltop, because they're going to be two separate signals. Well, we looked at that frequency, and it was exactly on the third harmonic. That could only be generated by the rusty bolt effect. Also, the rusty bolt effect could explain why we saw a 4.5 megahertz frequency difference between the video and audio carriers of that signal at the third harmonic of the signal, instead of seeing them spread 3 times 4.5 megahertz, which is 13.5 megahertz apart. Suddenly, it all comes together. It's got to be the rusty bolt effect. But now we're thinking, given that that's the case, can we confirm it? Can we do an actual measurement to confirm it? And the answer is yes. We went back up to the hilltop. This is in the cold of January in New England, and we did a direction finding exercise. We had a dipole antenna, and dipoles are very, very broad along a 90-degree line to the dipole's wire. But if you look at a signal directly off the end of a dipole wire, it will null it. So a dipole can be used as a terrific little direction finding antenna if in fact you're willing to not peak up the amount of power in the signal you're looking at, but null the power. You get a very sharp null in there. So we did this. We went up on the hilltop and we nulled, aimed a dipole back and forth until we saw the power at this earth station frequency on the hilltop minimize itself. It's very, very sharp. And we did this, if you imagine we're looking at a map, here's north, here's the broadcast TV tower, and we're sitting over here. We measure with the dipole and we get a null this way. Now, of course, it goes off either end of the dipole, so all we know is it's somewhere on that line, but it's not on the line where the tower is. Then we move ourselves over here, and we do it again, and this time we get we null on this axis. Well, if you null on this axis, and you null on that axis, the location where the signal's originating has to be where the two nulls cross, which is there, which is not on the broadcast tower for the television signal, and in fact was another tower. And that tower just had some point-to-point microwave transmitters on it and no land mobile radio transmitters, so nothing even operating in the VHF or UHF part of the spectrum. So this was the rusty bolt effect. It was a genuine, and yes, it was kind of a rusty tower, and so our hypothesis, was confirmed. We did some other follow-up work, but in essence, that confirmed everything at that point.
So you basically probed it. Right.
Yeah.
So that would have eliminated passive intermods in your cabling system.
And also eliminate
eliminate
passive intermods in the cabling system. So we reported our results to the agency. They didn't question the conclusiveness of the results, but they did say, so what now? You're telling us that the TV station is not at fault. It has nothing to do with their transmitter. It has nothing to do with the earth station receiver design either. This is coming from some rusty plate connections on a tower that's sitting off to the side doing basically nothing. What are we going to do? And our response was, why don't you wait for the DTV transition of February 2009 when they're going to take that analog signal off the air? Because your only other option is to really start to try to sort your way through that tower and figure out exactly what joint or joints on that tower are giving you a problem. And oh my gosh, talk about expensive and time consuming. So that concludes case history number 2, rusty bolt effect. Again, not a common thing, but not common doesn't mean never. It can happen. The point, I think, in all this is always be methodical if you're investigating an interference problem. You've got to walk your way through things. Don't assume anything. Prove everything. The very fact that interference is occurring means something's gone wrong somehow, somewhere. Nobody knows what. You've got to walk your way through and prove everything. Don't assume. Don't assume that everything was hooked up right. Don't assume that the transmitter is configured the same way as the block diagram schematic says it is. Check the transmitter yourself for how it's built. Use measurements, observations, and, as we were saying, when all else fails, logic to eliminate one hypothesis after another until finally you're left with just one remaining hypothesis, which, by definition, has to be it. And then, like we did with the rusty bolt, go up and confirm it. See if you can DF on a location that's not the transmitter tower. I mean, it should work. Keep good field notes, both for yourself and your sponsor, because I don't believe anybody, I know I can really remember after the fact all that much about what they did at a site. And finally, report your results and do it clearly and concisely so that everybody can understand your work and benefit from it. And then these are just some closing out references for this talk, measurement procedures for the RSEC, NTIA report 05-420, NTIA report 94-313, that discusses the front-end overload phenomenon and how to diagnose it, and a report on the resolving of the interference between the airport surveillance radar and the weather radar, which was our case.